Hello everyone, welcome to my next tutorial. In this video, we will be perform a tutorial enhance field intensity distribution using coating. So it is a fourth part of the video for the solar cell simulation topic. So before start of my video, I want to introduce myself. I am Sahil Verma, application engineer of the well-known company Impulse Technology. I have already told about our company's services. So who has not seen it my previous video, please check out the playlist. In this video, we will firstly discuss a small presentation, what we are going to perform, and then I will be show how we can enhance field intensity distribution using coating in the Setfos tool. Enhanced field intensity is the increase in the strength of an electrical field. O'Connor, one of the researchers, optimized the refractive index and thickness of a capping layer for two different OPV structures. We consider at here two structures and then we will consider different refractive index and their thickness, so we can evaluate how the field intensity increases. At here, Setfos reproduce the simulation and compare the maximum short circuit current to the curve found by O'Connor. You can see at here O'Connor results that published, and it is the Setfos results. You can see at here similar structures of the photocurrent with respect to the thickness. At the similar structure that you can see at here, we will be create in the Setfos. It is the second structures that we will be create. It is the layer names you can see at here, and the charge generation is compared between the result from O'Connor and Setfos as well. It is a charge generation results given by the O'Connor, and when we calculate at here Setfos software, so you can see similar results. In the first, the comparison between the maximum short circuit current can be say charge generation obtained from Setfos and the square electrical field amplitude as a function of the capping layer thickness, and capping layer refractive layer is seen at here. The similar result we will be seen in the Setfos tool. So now I am going to perform a tutorial in the Setfos tool. Click at here the right side and run as an administrator. About the Setfos, we have already discussed in my previous video how we can use Setfos GUI and how we can put input in the Setfos. It is a new features that available or update, so we can see it here. Once again, if I grew brief explanation about the Setfos GUI. For the create new simulation file, you can click at here. It for the your examples and path tab. If you want to save your files, you can save. If you want to save as, you can click at here. For the existing results, you can check at here. It is a passive optics modules, help to calculate reflectance, transmittance and absorption spectra only. It is a absorption modules, multi-layer optics modules calculation can be possible. It is a drift division modules where we can calculate all of the electrical parameters. It is a emission modules. It is a scattering modules which combine either emission or absorption modes. It is a master equation modes. Shift mode when we can variate multivariable can be shift at here. Optimization and fit emission zone. They both are used for the extract our parameter and got better accurate results. It is a general tabs, it's a layer structure, and that is the examples. For the create new simulation file, you can simply click at here, and otherwise you can see at here O'Connor examples. For your better understandings, I am going to create at here new files. You can easily understand how we can create O'Connor files and enhance field intensity distribution using coating. Click at here for the better view at both sides. O'Connor generally optimize the refractive index and thickness of the capping layer for two different OPV structures. So firstly I am going to create at here first OPV structure. At the similar Setfos, reproduce the simulation and compare the maximum short circuit current to the curve found by O'Connor. So now I'm going to create at here new files. You can add at here more layer through the plus I symbols. Now we need to provide at here one by one each layer name. Air, calcium monophosphide, it is an inorganic compounds. Ag, aluminum first, C60, It is a carbon electrode bulk minister fullerene. CuPC name copper thiocyanide. We need to add at here one more layers, that's name aluminum. Second, glass. Now we need to provide at here thickness 50, 8, 3, 50, 75, glass 0. Top and bottom layer are semi-infinite medium, so thickness are irrelevant at here. We need to provide at here refractive constants because we are going to optimize the refractive index and thickness of capping layer. If you click at here, you can see layer structures. It changes according to the thickness. You can see at here the variation. For the air, it will be 1. We are considering at here the same as tutorial, so you can got same results that you seen in the Setfos tutorial, and it will be matched according to the O corner results. 0.13, 0.69, 2.2, 1.6, 0.69, and 1.42. At here we also need to provide these value 3.07 for the aluminum first, 5.7, it will be same as aluminum, 5.7. We need to activate absorption module. You can see at here the shift wavelength according to the energy. We are considering at here single wavelength and it will be 470. Illumination spectrum files, it can be white, location and times. If you select that, first give the ability to calculate all of the parameter of the absorption according to the date and with respect to the timing. But we need to import at here sun spectrum files. At here number of the files are present. You can see at here data column it will be 2. We need to activate shift modes because we are going to shift our parameter of calcium monophosphide respect to the thickness. You can check at here number of the optical parameters are given. With respect to you want to shift, you can easily consider any one of these and can be shift according to these parameters. I am going to shift at here thickness of calcium monophosphide. Ranges it will be 2.5 to 200. Step it will be same 2.5. At here you can shift according to the log elements log random logs list file as previous, but I am considering at here only linear. Now we need to provide at here your simulation files. O'Connor 4. Layer structure are completed. Absorption settings are also completed. Shift setting you are also considered at here. Calcium monophosphide thickness. We can simply click at here play button. You can see at here your results. It is a photocurrent, stacked contribution photocurrent. Optical profiles are also given. It is a absorption profiles, energy plus, generation profiles, illumination spectral absorption profile, phase, refractive index, and white spectral absorption profiles. At head absorption, layer absorption, reflectance, state contribution, and transmittance. You can see the comparison between results from the O'Connor and Setfos are presented. We see that thickness corresponding to the highest and lowest short circuit current matched with the results O'Connor. You can simply click at here and hide these layers one by one. Now hold and zoom like this. The similar results you can compare with the O corner. You can click at here help and Setfos tutorial. You can simply give at here name solar cell application. It is on the 69. Simply click at here 69 page and type. It is a solar cell application. You can see at here the similar structures, the comparison between the result O corner and Setfos that's presented at here. Maximum short circuit current as a function of capping layer of OPV structure. The simulated maximum short circuit current obtained by Setfos for the same structures. Now we will be back in the Setfos GUI for a similar structures consisting of air script given the charge generation is compare between the result from O'Connor and Setfos as well. So simply click at here the create new simulation files and add one by one each layer name of the create second OPV structure for the compare charge generation profile. Air, calcium monophosphide, Ag, copper thiocyanine, allotrope of carbon, Buckminster Fuller, BCP known as bromocresol, purple, aluminum and glass. Now we need to provide at here thickness. It will be 50. For the silver it will be 9. Copper thiocyanine it will be 20. C60 it will be 40. Bromocresol 10. For the aluminum it will be 70. Top and bottom layer are semi-infinite medium, so thickness are irrelevant as same as previous. Now we need to provide at here refractive index value. For the air it will be same one. Calcium monophosphide it will be 5.3. For the silver it will be 0.13 and at here it will be 3.07. 1.6, 2.2, 0.35, 1.8. One by one we will be provide each of the value same as tutorial 0.69 and 5.7. It totally depends on your project which value you want to consider at here. For your understanding I am considering at here same examples value. Now we need to activate at here absorption modules. You can shift at here wavelength 469 to 471. Step at here will be 1. Illumination spectrum files it will be same and data column it will be 2. At here wavelength 470. Now we need to activate shift modes because we are going at here shift parameter of the calcium monophosphide refractive index and calcium monophosphide similar thickness. First we need to consider at here that value. We can add at here more shift parameters through click the plus symbols and similar we can add at here thickness parameter. Ranges it will be minus 0.95 to 3. Step at here 0.1, 5 to 150 and step it will be 5. At here layer structures are completed, absorption settings also completed and shift settings also have completed. Now we need to provide at here your simulation file name. Click at here play button. We can see at here results optical integrated photocurrent, stacked contribution photocurrent, passive optic properties. Click at here one by one. You can see at here reflectance, reflected color, transmittance, transmitted color, absorption, layer absorption, reflectance, stat contribution and transmittance. You can change at here x-axis respect to the thickness of calcium monophosphide and that value also. If you play at here button, you can see at here the variation. It will be same for each. The comparison between the maximum short circuit current at her charge generation obtained from Setfos and the square electric field amplitude as function of capping layer thickness. You can see at here the comparison between the maximum short circuit square electric field amplitude as a function of the capping layer thickness and refractive index obtained from O corner. The maximum short circuit current or charge generation obtained from the Setfos. And check out here that parameters. If you zoom like this, you can see at here the variation. Click at here the log, apps, inverse if you want. Basically, overall calculation is that Setfos tools help to work on the research. You can validate your results with the help of the Setfos tools because most of the researchers publish their paper with the help of the Setfos. Now I'm going to end at here my tutorial. If you have any query related to this, please ask in comment box, and in the description box email are also given. You can visit our website impulsetechnology.in for the book or demo, and who has not seen it my previous video, please check out the playlist. It will be helpful to use our Setfos tool. Thank you very much.